Hi guys, welcome back. I hope you guys are doing as good as can be expected. We are going to start Flexure today. So Flexure, remember we're talking about is bending, so beams. And specifically we're talking about moments, not shear. We'll touch on shear at the end of this, but this is about designing a beam, steel beam for a moment. We're going to talk about how yielding affects that, some plastic, some section medulla. Anyway, all that stuff up there, all those words. By the end of this lecture, you should be able to understand what those things are. So, this is a beam. Let's say we have a beam. It is what is the definition of the beam? It is a structural member. Subjected to, like we just said, bending and shear. Right? You might have a moment on one end, a moment on the other end, right? Let's say this is a beam with, right, some type of distributed load. It's got a moment on one end, a moment on the other end, shear on one end, shear on the other end. And that results in positive bending, right? Positive meaning happy, meaning it bends this way in a smiley face. And I'm going to take a little section. Nope, that's not what I wanted. I'm going to take a little section, right? And I'm going to look at this little section. Okay? So, I have a little section, and I've got positive bending moments, or moments causing positive bending. And what do I have on top? What kind of stress is that? It's compression, right? And the stress on the bottom is tension. The strain causing compression on the top, tension on the bottom. We're going to make a couple of assumptions. One, that we remain linear elastic, initially at least. That there are no residual stresses. Do you guys remember residual stresses? That means there's already some stress in parts of your beam, in elements of your beam, meaning They don't need a little bit more before they get to yield. Things will start to yield unevenly. For now, we're assuming that there aren't any of those. And we're going to assume that plane sections remain plane. So no weird, funky distortions. Everything kind of acts as one plane. These are the planes. So if I draw, you might remember all this from mechanics of materials. If I draw the strain profile, right, it looks like it's a linear, right? If this is my plane section remaining plane, it's a linear displacement, right? And displacement is directly related to strain. So it's a relationship that's linear. So I'm going to draw a strain profile like that, where I have compression strain at the top, tensile strain at the bottom, right? Because I'm in tension and compression. And neutral, no strain, no displacement at the middle of my beam. You could also say that these are equal. The strains are equal. And if we all remember our mechanics of materials, stress is equal to the elastic modulus times strain. So if I want to draw that, it's the exact same. Same shape, that is. Different values, right? My stress is equal to my elastic modulus times my compression strain, and my tensile stress is equal to my elastic modulus times my tensile strain. And right now those are equal. So the extreme tensile fibers are extreme compression fibers, extreme contention fibers, where we have the highest stress should be seeing the same stress, except one's in tension and one's in compression. This is all review for mechanics of materials, I hope. That's how we relate moment to stress and strain. You might also have learned, well, we'll go back to that, the actual equation. So talking about plane sections remain plane, that's in the next one. That means if I have bending, like this is my cantilever, and I look at this plane, and I look at this plane, they're straight, right? Nothing's doing anything funky. So that assumption means that the strain varies linearly over the height of the cross section. Right, that's just what we drew before. If we look at the cross section, my strain is going to look like this, a straight line. Versus something like that. Ding, 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 ding. Okay, that's all that means. It means we're not, doing something like that. The plane, the cross section that you're looking at doesn't, different parts don't start going displacing more than others within the cross section. Okay? Now, we've gone back to this a bunch of times, right? This is my stress strain curve of steel. We have the elastic range, right? But then that neglects everything past it, right? It neglects, that's not what I'm trying to do. It neglects everything from here on. Okay? So, in flexural design, since this right is so not pretty looking, right? We make a simplification and we say, let's just assume that it remains elastic and then perfectly plastic. Once it hits yield, it isn't allowed to have any more stress in it. It doesn't have any more strength. Once it hits yield, that's the highest stress that a little minuscule molecule of steel can take. This is called elastic, because it's elastic, up until that point, and then perfectly plastic. Okay? That means once it hits that yield stress, Fy, it doesn't go all the way up to Fu. Even though it theoretically might be able to hold a little bit more stress, have a little bit of strength left in it, we're not gonna say that it can. So elastic, perfectly plastic. So what does that look like as we are loading our what does that look like as we're loading our beam? On the top, I'm going to talk about increasing strain, and on the bottom, increasing stress. So my first step, number one, I'm going to apply some amount of strain less than the yield strain. So I have some strain, and it's some stress equal to our elastic modulus times the strain. Right? Well, you keep applying strain, and eventually you get to the yield strain, which is your yield stress over your elastic modulus. And again, I'm assuming the top and the bottom of the cross section are the same, so I'm only going to look at one side. Okay, well, I've looked at the yield strain, or I've hit the yield strain, so now if I look at the stress profile, I've reached the yield stress. And we just talked about how we can't get any more stress than that, right? So now I'm going to keep applying strain, right? That was number 2. Number 1 was you are applying strain in the elastic region. Number 2, you reach yield strain. Well, now something hits yield, it can't have any more. It can keep straining, it can keep displacing, but it can't have any more stress. So, right about here it hits yield strain. If I keep applying my load, but that whole section can't take any more stress, right? If from here below and from here above, this part of the cross section has yielded. Meaning it has hit yield stress and it can't go any further, right? But it can keep straining all at once. It can keep moving, right? If we go back, you can keep applying strain all you want, right? But, right, this is me applying strain. Right? Keep applying strain. It just won't get any more strength out of it. The stress won't increase. So part of the cross section has yielded in part 3. But it keeps displacing. Strain keeps going. Well, if I apply more, again, now we're up to, what is it, about here? Only the tiny little part in the middle of my cross section hasn't yielded, right? This is all yielded. This tiny part in the middle. It can keep displacing. The strain can keep increasing, but it won't yield. But it won't increase strength, I mean. And eventually, you keep adding enough strain to where you've yielded the entire cross section. Number 5. Well, what does that strain profile look like? A flat line, right? Infinite strain. It just keeps going. Also known as a plastic hinge, right? Up until you hit yield, you're in the elastic zone. Once you hit yield, you're in the plastic zone. And eventually, enough of your cross-section has yielded that you've created a hinge. It's technically still connected, right? But you're just going to be bending around that hinge. It's a hinge now. It's not holding anything up. So you lose stability. So the parts that we care about, there's 2 moments that we care about the most. This moment, number 2, called the yielding moment. And that is where outermost fiber begins to yield. So you're just starting yielding at the very, very edges of your cross section. That's the yielding moment. And then when your entire cross section has yielded, that's called the plastic moment, because you've just created a plastic hinge. Right? Before the yielding moment, this is purely elastic behavior. After the yielding moment, you beyond elastic, right? I don't want to say plastic. Right, we're starting to get into the perfectly plastic, but not all of the cross section at the yielding moment has yielded. So, and it's not until the entire cross section is when you get the full plastic moment. The yielding moment is just when your outermost fibers, if you're in an I-beam, you're talking about the very top of your flanges, the bottom of your flanges, and then your entire cross section has yielded. Is the plastic moment, and it's a milestone you don't want to hit, right? It's kind of like yielding versus fracture when we're talking about tension. Now we're talking about yielding versus plastic moment, right? So that's the evolution with increasing load, increasing strain, resulting in increasing stress. How that evolves from elastic to a yielding moment and then all the way to a plastic moment. Just to remember thinking an idea of what a plastic hinge looks like. If we're looking at a beam and it develops a plastic hinge, now if you apply a load, you're going to deflect like that, right? And this is unstable. Excuse me, I just burped. Okay. So our shape factor is something that we have to calculate. And it is the relationship between our relationship between our plastic moment and our yielding moment. Okay, I'm going to stop that right there. Just for a second, let you guys digest that, and I'll come back in a minute with calculating yielding and plastic moment.